So let's spend a bit more time looking at this financial model that we've been working with in previous videos. This is an investment account, and the model is A of t equals 500 times 1.04 to the t, where t is the elapsed time in years after January 1st, 2018. Just a reminder, 500 is your initial value, and 1.04 is your growth factor. Let's write that down. Therefore, 0.04 is R. That's 4% growth rate. I might not need that for this question, but it's good to continually remind yourself of what these things are. So this is B, and that's R. Okay, so moving on. So question A, by how much does this balance increase every 5 years? So notice that that's saying every 5 years, not just in 5 years, but if we jump forward in 5-year increments, how much does this balance increase? So this is like a chart that we need to look. We need to make a table, right? So I've actually done this already. So we've got this table here where we've got yearly increases. So here we're going 1 year, 2 years, 3 years, 4 years. And so we'll do the 5-year in just a moment. But what I want to point out right now is notice what we've got here. So we have 1 year jumps here. Then you've got your increase in the function. But this is the important thing. In this third column, I've got the ratio of the new value divided by the old value, where we move forward 1 unit. And if you recall what the definition of the growth factor was, that for every 1 unit that you move horizontally, the output of the function will get multiplied by the growth factor, and so that will be the new value of the function. So in other words, you would have the old times 1.04, and that's going to be the new value. But then when you divide that by the old value, those just cancel and you're just left with 1.04. Hence all these numbers. Okay. Now, in this fourth column, we have the average rates of change. And you notice that these are not constant, right? So this is not linear, so we don't have a constant average rate of change, but we do have constant ratio of new over old outputs. So when you're looking at a data set and trying to decide whether or not it's exponential, this is really what you look at, is this ratio, and then they need to be the same, okay? So maybe one more thing about the average rates of change. They're not linear, but they are increasing and positive, right? So we know that the function already is a increasing and concave up, and that matches these numbers, okay? All right, so now let's look at the 5-year change. 5-year increment. It's supposed to say increment. So I'm jumping in 5 years, okay? And we have our corresponding function values. And we've computed the same ratio. In other words, what is the new value after 5 years divided by the old value the previous 5 years? And then we did that for each one of these. And notice that they're all the same, but they're not what they were a moment ago, right? So we still have this constant ratio, but it's a new ratio, which makes sense because we have a new, it's a new leap that we're taking, right? We're leaping forward 5 years rather than 1 year. And the average rates of change are still increasing, non-constant, okay? But going back to this, as it says down here, for a fixed t-axis interval, ratios of successive values are constant. And when delta t is 5, that constant ratio, what is it? Well, we just take 1.04 and we raise it to the 5th power. And that computes to 1.2167. So these values that you're seeing here are actually b to the 5th. They're all 1.04 to the 5th power. Okay. And the interesting thing about this is that we can now think about this as a 5-year growth factor. So we could actually create like sort of a new model that was a 5-year model. And sometimes that's useful. You know, if you need to change the time unit because, say, maybe 1 year is too small of a time change, and the real change happens every like 30 years or something, well, then we could do that. All right. So that's our 5-year growth. Let me go back to the problem. Question B says, by how much does the balance increase every 6 months? Okay. Well, we've done a little work on this already in the 5-year zone, but first of all, 6 months is half a year, so that's 0.5 years. So what about just after the first 6 months? Well, after the first 6 months, we would have, what would t be? Well, it would be 1/2, right? That would be half of a year. And if we did this again, and then we went for another full year, so we would probably for a whole year total, but just advancing forward another 6 months, this would become the new input, and then this would get multiplied again by 1.04 to the 1/2. And every time, so what you're looking at now is a chart of all this behavior. So every time I move forward 6 months, I would multiply the previous value by 1.04 to the 1/2, or 1.04 to the 0.5. And that is equivalent to the value 1.0198. And that's your constant ratio for a 6-month growth. Again, average rates of change, not constant, but increasing. But what we have now is a 6-month growth factor. And we get it by taking the original growth factor and raising it to the 1/2 power. All right, I think we have one more. By how much does the balance increase every 17.67 years? Well, I've got that information right here. And it works out to be the same sort of stuff as we were doing in the previous tables. But, you know, as you can see, this is kind of a weird value, right? 17.67. So what's important about that? Well, you may remember from a previous lecture that we actually found this value to be the doubling time already. And if you recall, when I was discussing doubling time, I said the doubling time is constant. So if you have a doubling time of 17 years, then that's always going to be the time it takes to double, no matter how much you had. So here we see that every 17.67 years, we have twice what we started with. So A increases by a factor of 2. Okay, so in summary, what all this is kind of adding up to is that we are messing around with changing a 1-unit growth factor to some other unit growth factor. So we talked about going from a 1-unit to a 5-unit, from a 1-unit to a half-unit, from a 1-unit to a doubled unit. You see some other ones in this table. You've got a 10-year unit, and in each case, all we have to do is we take B and we raise it to the appropriate value. So we raised B to the 5th, we raised B to the 1/2, we raised B to the 10th here, Here we raise b to the 17.67, which is, that's the doubling time, etc. Okay. And then you've got some other ones computed here. The third column, this is actually calculating rates for each of these. So this is our original annual rate, growth rate. So what is this? Well, this is this value 1.2167, and then we subtract 1 from this and multiply it by 100, and then we have our 5-year rate, 5-year growth rate. This would be our 10-year growth rate. Etc. Okay. So in each case, notice that the important thing is that the first thing that we do is we convert the growth factor. And then we can get this new growth rate. So we start with the growth factor, we raise the growth factor to the appropriate power, and then once we've raised that to the appropriate power and got this new value, then we can get the growth rate by subtracting 1 from it and multiplying by 100 to get percent form. So that's what this is talking about, this r equals b minus 1. You do this first and this second. Okay. All right, let's move on. Let's look at an example where just another exponential example, and do some more work with exponential functions. In 1966, the average cost of a gallon of gas in the U.S. was 32 cents, and we're going to assume this average cost to be the middle of the year. Between 1966 and 2006, the cost of a gallon of gas increased at an annual rate of 5.5%. So here's our data for our function, and then our first task is to write a model for the cost of a gallon of gas in dollars as a function of t, the number of years after July 1st, 1966. So again, this is an elapsed time model, so we're resetting the clock. I know it's going to be an exponential model because I am given a rate of growth. Okay. And so my exponential growth model, we actually kind of have a couple of choices of how to start with this. We have this form, and we also have this form, which they're equivalent, but sometimes one is more useful than the other. In this case, this is the form that's most useful because I'm given an R value. So R, if this is 5.5%, then R is going to be 0.055. Therefore, B is 1.055. Okay? And my model, A of t, will have our initial value, which is 32 cents. So that's 0.32 of a dollar times 1.055 to the t. And that's our answer for part A. So there's our model. Okay. Question B says, according to the model, in what year did the cost of a gallon of gas reach $1? Well, this is an output, and we're looking for an input. So this is going to be a calc-intersect question. So I'll need to type this function in. And I think I'm going to actually pause the video now, and we'll finish this up in the next video.